In this video, we're going to be doing a Unit 5 rotations FRQ for a person on a platform. So imagine that a person of mass m stands at the center of a rotating merry-go-round platform of radius r and moment of inertia I. The platform rotates without friction and with an angular velocity omega initial. The person walks radially to the edge of the platform. So we want to derive an expression for the angular velocity of the system when the person reaches the edge. That was their initial position. This is their final position. What we can do is we can see that we have no external torque because this is going to be our system. We're considering the entire merry-go-round platform as our entire system, the rotating merry-go-round platform. So energy and torque that is occurring at different points of this merry-go-round is not going to exert external torque. So if there's no external torque, we can say our change in angular momentum is going to be constant. So it's conserved. We can write our initial angular momentum. So if the person is at the center, that means that they have no contribution to the moment of inertia. So you can write on this side I omega initial. So for our final moment of inertia, that means that we have the inertia of the person is now at the edge. When you're at an edge or you have a mass that is being rotated at an edge from an axis, that is basically like you have a hoop. This is the same thing as a hoop, and this is the same thing as a mass that is just being spun in a circle like this. Because this person's always going to stay at that radius. Same thing for a hoop. The mass is always going to be at this edge. So that equation is the mass times the radius squared. So in total, in the final position, our inertia is I plus mr squared. So we set them equal to each other, and then we solve for omega f. So this is our final expression for omega f. So what you can see that if you increase your moment of inertia, that is going to decrease your angular velocity to conserve your angular momentum. Because again, our basic equation is angular momentum is I times omega. Now for part 2, we're asked to consider the system consisting of the person and the platform. Find an expression for the change in the kinetic energy of the entire system and explain where the kinetic energy came from or went. So we're finding delta K. Well, our initial kinetic energy is 1/2 I times omega initial squared, and our final kinetic energy is 1/2 I plus the mass times radius squared times omega final squared. So if you substitute in what we had for omega f up here into our current equation, well, then you're going to get that. Well, first, before we do that, let's just square it. So omega f squared would be I over I plus mr squared omega initial squared. So let's substitute this in instead. Our equation is 1/2 I plus the mass radius squared times I squared over I plus the mass radius squared times omega initial squared. So you can cancel out one of these. we're still left with 1. So then we have 1/2 times I squared, I plus mass radius squared, omega initial squared. Now we can find delta K. So delta kinetic energy is equal to Kf minus K initial. So delta kinetic energy here is equal to our final kinetic energy, this expression here, minus our initial kinetic energy, which is this expression here. So what we can do is we can factor our common terms. Then we can simplify our bracket. So for this really complicated fraction, we can just rewrite this as something over 1. So this would just be I minus I plus m r squared over I plus m r squared. That's because when you have 1, that's the same thing as writing anything over itself. And then if you have so this is equal to 1, right? And then if you have 2 things with the same denominator, then you can combine the denominator, which is how we got this. So then your final expression for delta K is 1/2 I omega initial squared negative m r squared 1 or I plus m r squared. One more thing we could do is just combine this into one fraction or make it visually easier to look at. So what you can see here is that your delta kinetic energy is going to be less than 0, therefore your kinetic energy decrease. And where did it go? Well, our energy is going to be converted into internal energy, which is consisting of muscle work and also heat. The person must do and move outward against the effective rotational inertia. So increasing your radius is going to decrease omega and also decrease your kinetic energy. Again, we had no external torque and our angular momentum stayed constant, but our internal forces are changing our energy. And again, going back to omega F is going to decrease and is less than omega initial because inertia initial was less than inertia final. And also, if you look at this component as well, this quantity is going to be less than 0 because I over I plus mass radius squared is going to be less than 1. So that's also how we see that kinetic final is less than kinetic energy initial. And energy dissipated into thermal.